Hello, kids. Mr. Johansson here. Let's look at mechanics number 15. We're talking projectiles now. We just did 14, which was a cliff problem. And if you think about a projectile, right, when a projectile is fired, when it's going up and it reaches the highest it's ever going to get, isn't that moment exactly like a cliff problem? Its initial velocity, vertical, is 0, right? It's right at the top. Its up and down velocity has gone to 0. So now it's just a projectile with a forward velocity that's going to fall in a certain amount of time and then hit the ground based on the time multiplied by its forward velocity. So that's what a projectile problem is. Oh, you guys want to read the quote, don't you? Nah, we didn't do the quote on 14, so let's hit the 14 and 15 quotes. Sir Edmund Hillary said, "It is not the mountain we conquer, but ourselves." Okay, you're studying physics. Physics is hard. You're not going to conquer physics. That's not what you're conquering. What are you conquering? Yeah, you're getting yourself out of your own way to study hard things. So every mountain, whether it's real or metaphorical, that we climb, we don't conquer that mountain. We conquer our own selves. And that is the big battle. Hillary was right. What a brilliant thought. And how about mechanics 15? Here's a quote for you. "Science is a first-rate piece of furniture for a man's upper chamber, if he has common sense on the ground floor." That's Oliver Wendell Holmes said that. So science is a great, great thing to have as an awesome thinking tool, provided you also couple it with some basic common sense. Well, you could chew over those quotes all you want. Let's get to some projectile problems, shall we? So I've drawn one on the board behind me here. 32 degrees and 1,000 meters per second. Well, what do we need to do? First thing we need to do is determine the time it's going to be in the air. Because the up and down component of this, your vertical velocity, whatever that is, that's going to govern how long it's going to be in the air. However many seconds that's going to be in the air, that's going to stop it. When it finally hits the ground, that's going to stop it. Okay? So here, we will use this to find the time of flight. Okay? We have enough givens to do that. Down here, we will use this to find the actual distance. When we multiply whatever the velocity is that we have in the horizontal times the time we found here, that will give us the total distance our projectile went. So the first thing is to break it into your horizontal and vertical axes. So how would I get my vertical axis first? All right, well, how about 32? Well, would this be cosine, sine, or tangent? Well, that's the opposite from the hypotenuse. So we have sine function. So 32 sine times 1,000. So we have 530 meters per second. 530 meters per second straight up. How long until it comes to a halt? Come on. Come on, talk to me now. How long till it comes to a halt? You know this stuff. What is its speed being reduced by? Right, 10 meters per second every single second. So if it's going 530 meters per second, how many seconds till it comes to a halt? About 53 seconds. Good. How many seconds till it's back on the ground? Another 53 seconds. How many seconds total? 106 seconds. Great. So you know your time. It's not going to be dead on, but it's going to be really close to 106 seconds. How do we do that? All right, well, we'll get there. Let's look at what we would find for its horizontal velocity, shall we? How do we do that? Cosine. Thank you very much. So 32 cosine times 1,000. That's 848 meters per second. 848 meters per second. 848. All right, let's go to the other board. We're going to turn this into vertical givens and horizontal givens. But it's going to take something more than a little bit more board space than we need. So come on, we're going to the other board. My, look at that. We're at the other board. All right. Well, thanks for coming along. Here we are at the other board, and we want to write down givens, vertical. What do we have? Well, we have initial velocity of 530 meters per second. What is my final velocity on impact going to be then? What's my final velocity on impact going to be? All right, my final velocity, it's going to be negative 530 meters per second, right? It was going up at 530, going to be coming down at 530 meters per second. My acceleration is going to be negative 9.8 meters per second squared. My time, that's what I would like to know. All right? So my formula. What do I have? Acceleration equals change in velocity over time. Time equals my change in velocity over acceleration, and that's VF minus VI over A. Sub the numbers in. What do we got? So we have negative 530 meters per second minus 530 meters per second, all over negative 9.8 meters per second squared. Handy dandy calculator. So what do we get? 530 minus 530. You can kind of see where all of this is going. That's negative 1,060 divided by 9.8. Make that negative, and I end up with 108. How do the units work out here? Well, meters per second. The meter cancels meters. That second cancels that second. That's in denominator of a denominator. When we invert and multiply, that's at the top. So 108 seconds. All right. And now I go to my givens horizontal. All right. So we know this object is going to be in the air for 108 seconds. So time equals 108 seconds. My velocity, now that's my horizontal velocity. We found that to be 848 meters per second. 848 meters per second. Is that changing? No, there's no acceleration horizontally. So we have a time, we have a velocity of 848 meters per second. And I want to know my distance. So the formula, velocity equals distance over time. Distance equals velocity times time. Okay? And my S and S, distance equals velocity times time equals 848 meters per second times 108 seconds. That's 91.7, well, let's do the whole number. 91,722 meters. All right? That's getting a little silly, isn't it? That's a lot more numbers than I have a right to report here. 91,722 meters. Well, we know there's 1,000 meters in a kilometer, so it would be most appropriate, using significant figures, the smallest of which has 2 numbers in it, would be most appropriate to say something along the lines of 92 kilometers. That object would land about 92 kilometers away, if all that was correct. All right? So that's how we do these projectile problems. You have givens, you break it into vertical and horizontal. Vertical has acceleration to it. Just draw a free body diagram, you see that. Horizontal has no acceleration with it. So we use the vertical to figure out how long it's going to be in the air. Your initial velocity is going to be exactly the same as your final velocity, just your final velocity is going to be down, so it's negative. Make your gravity negative, and that'll cancel out. Your time, of course, has to be positive. So we have this vertical stuff we use to find the time of flight. Then we just multiply it by what our horizontal velocity is. The real screw up is if you use anything from that initial triangle. If you use this data, 1,000 meters per second, this is not going to work out for you. It can't work out for you. You have to break that into your initial vertical velocity and your horizontal velocity. Why don't I say initial horizontal velocity? Because your horizontal velocity, once again, doesn't change. That's the key stuff in a projectile problem. So work on it.